What you may have missed in the last episode. This week's overview. Today we will be going deep into the process of rigor mortis. This is where muscles in the body harden directly after death.
Hi, my name's Anna Garcia. You may remember me from last year. The reason I'm in this odd position is because of rigor mortis. I was like this for the 46 hours after my death. You may be asking yourself, what is rigor mortis? Well, before we get into that, let's explain a muscle fiber before death.
To fully understand a muscle contraction, we need to go over the basic terminology. First, we have the axon terminal and the neurotransmitters. We move on to the sodium ions, which leave through the sodium channels. Then there's the sarcolemma, and below that is the T-tubule. The T-tubule holds the terminal cisternae with the calcium ions. To the right of the actin is the Z-line. This is the actin. Next, we have the actin binding site, which has troponin, which pulls on trypamyosin. Here's the myosin head, and finally, here's the M-line.
So let's look a little deeper into how a muscle fiber contracts for movement. The true actions lie inside of a small section of the muscle fiber called the sarcomere. Where the sarcomere meets the motor neuron is called the neuromuscular junction. This is where the signal is sent when the body wants to move. First, an action potential is sent through the motor neuron down to the transmitters.
Oh, is this like the action potential with the sodium and potassium pump?
Exactly. Because of the action potential, the neuron transmitters then go down into the synaptic cleft.
And the synaptic cleft is the area between the motor neuron and the receiving neuron, right?
Yes, of course. We can't forget about that. Once the neurotransmitters are there, they signal for sodium channels to open up, causing the sodium ions to flush through the channels, creating another action potential.
This action potential then travels down along the sarcolemma.
Whoa. Slow down. What's the sarcolemma? That's new.
Oh, yes. Thank you for catching that, Anna. The sarcolemma is the membrane of the muscle fiber.
It has specialized functions for muscle cells that help the muscle fibers.
One of these special features include the T-tubule, which is what the sarcolemma forms that leads the path to the calcium.
The axon potential travels down the T-tubule. The branching off the sides of the T-tubules are known as sarcoplasmic reticulum. These are responsible for holding the calcium ions. Once the axon potential travels down the T-tubule, it signals for the sarcoplasmic reticulum to release the calcium ions down the T-tubules and to the actin.
So is the actin the thick or the thin filament?
That's a really good question. It is the thick filament, and at the actin, the calcium binds to the troponin of the actin, which causes the trypamyosin to turn. Do you know what that does? That's okay, you wouldn't have learned that in biomed. It reveals the actin binding site. Then ATP comes and binds to the myosin head. This time, the myosin head is a part of the thin filament. The break apart of the ATP into ADP and a phosphate group causes the myosin head to change from its low energy configuration to its high energy configuration and binds to the actin binding site.
This then creates a bonding site between the cross bridge and the myosin head. Once the myosin head relaxes, it drags the myosin closer to the M-line.
The M-line? What's that? Is it like the middle of the sarcomere?
Actually, that's exactly right. And the Z-line represents the sides. This provides the action of moving the Z-line closer, which occurs because the cross bridge is still intact, so it allows it to be dragged along for the ride. This is called the power stroke. Contrary to what many people think, it does not require energy.
Wait, I thought ATP was required for it.
Not exactly. The ATP is required to move the myosin head, but the actual power stroke is just a result of the relaxing of the myosin head from the high configuration to the low energy configuration.
The only way for the cross bridge to be broken is for ATP to come once again and break the cross bridge.
For rigor mortis, what happens is since the brain cannot control the amount of sodium being let out, all the calcium gets let out at once, creating contractions. However, they cannot be broken because there is no more oxygen to create more ATP. So there is not enough ATP to break apart all the cross bridges. So the muscles are left contracted until the bacteria and enzymes in your body break apart the cross bridges. This can often take a couple of days.